So I was going to talk about two kinematic concepts related to rotation. The first one we talked about earlier was irrotational flow when the vorticity is 0. The second concept is circulation. And we encountered this briefly in the tensor chapter when we were looking at Stokes' theorem. So the circulation around a closed loop is written by capital gamma and defined as the integral around the closed loop of the velocity vector dotted with the tangent of the loop vector. And that, from Stokes' theorem, is the same as the vorticity vector omega dotted with the normal to any closed surface for which the contour C here is the bounding loop. And this follows from Stokes' theorem. And I encourage you to go back to chapter 2 where we showed this and discussed this earlier. And the circulation per unit area, gamma over A, if we consider the limit of a small area, limit of A going to 0, then in this case the integral over omega dotted with the surface, and again the surface can be any surface that's bounded by this C, that goes to simply omega dot n. And so this is actually a way of defining vorticity. This is the circulation per unit area. Yeah, so vorticity is essentially the degree of rotation around an infinitely small loop, i.e. around a point. And alternatively, we can write this as n dot omega is the limit of A going to 0 of 1 over A line integral u dot ds. So, for example, consider a flow field that's uniformly in one direction. So these are our u vectors. And now we consider, so this is u. And now we consider some closed loop around it. Let's say we'll go counterclockwise around here. And now we can piecewise do, so up here we have positive and negative contributions, and we piecewise do the integral u dot ds. So for the top line here, this integral here will be u dot n, which is going to be minus the magnitude of u, and I should say here this is a constant magnitude unidirectional flow. Whereas down here for this line element we have u dot n is positive, just the magnitude of u. For the two sides, we know that u dot n is 0. So as a result, the integral u dot ds is minus u plus 0 plus 0 for the four sides, which is 0. So there's no circulation in this flow. Let's consider a different example. Say we have a velocity field that flows to the right in the lower half of our domain and to the left in our top half. So in this case, if we consider the same boundary loop and again integrate in the counterclockwise direction, then now we actually have up top, we have u dot n equals u, the magnitude of u, because now the flow is in the direction of our integral. And down here we have u dot n is also u. So that's for the bottom half. Whereas on the sides again, we have u dot n is 0 on both sides. So when we add this up, u dot ds, then we get u plus 0 plus 0 is 2 magnitudes of u. So now you have a positive gamma, positive circulation in this flow.